This video will explore the basics of memory management in C++. Anytime a variable is declared, some memory is set aside for it. This setting aside of memory for special use is called allocation. Your program's available memory is conceptually separated into two main parts, the stack and the heap, which correspond to automatic and dynamic memory allocation. For global variables and other variables that specify it, there is also static allocation. A variable only exists within a certain scope, depending on where it is declared. A variable declared outside any function, struct, or class is in the global scope, meaning that it can be accessed anywhere in your code. These variables are allocated when your program starts and are deallocated when the program exits. The scope of a non-global variable is the innermost block it's declared in, blocks being defined by the use of curly braces. A variable's scope could be a function, an if statement, a loop, any set of curly braces. Once code execution moves past a certain scope, for example the end of a function, the variables that were declared within that scope and allocated on the stack are deallocated. This is the nature of variables on the stack. They are automatically allocated and deallocated. You aren't responsible for handling their memory use. This makes them easy to use, but also of limited usefulness. You can't count on them to stick around. For example, consider the following code, which contains a programming error. The function returns a pointer to a variable declared on the stack, which then becomes invalid as soon as the function exits. Because of the error in this code, its behavior is called undefined, meaning that the C++ specifications don't define a way for it to be properly executed. Therefore, we can't say in an abstract sense what should happen when this code is compiled and executed. But we can, in practice, compile and execute the code and see what happens. And apparently it's this. In main, an int pointer variable is created on the stack. Its value is set to null. Next, the getPointer function is called. This function creates a variable on the stack, sets its value to 42, and then returns a pointer to that local variable. This is the bug, returning a pointer to a local variable. As soon as the function exits, the local variable is deallocated. The variable ptr points at the spot in memory that in used to occupy. But that memory has been deallocated, meaning that the computer is now free to reuse it. It is therefore no longer strictly safe to dereference the pointer. However, if the pointer is immediately dereferenced, it will still hold the value 42. But now another function is called. All this function does is declare a variable on the stack, assign it a value, and then exit. When it exits, the memory that was allocated for the variable will be freed up again. But in the process of allocating and initializing a variable on the stack, the memory that had previously been used for in, and which ptr still points to, gets reused. When ptr is then dereferenced, the memory pointed to now holds the value 12. While this behavior is somewhat predictable, it can't be relied upon. There is no way it should work, so another compiler could implement the memory management differently. Some compilers will warn you that returning the address of a local variable is a logically incorrect thing to do, although it is syntactically allowed. Like dividing by 0, you can ask the computer to do it. You just shouldn't. So how can we fix the previous code? We can dynamically allocate memory by using the new operator. This memory will persist until we explicitly deallocate it using delete. The new operator allocates a chunk of memory on the heap and returns a pointer to it. This means that whatever type you specify with new, the result is a pointer to that type. In getPointer, now we'll declare an int pointer variable to store the result of calling newInt. In our revised example, you see the correct way to allocate and deallocate memory. It omits the code that dirties the stack, but it would still work even if it was included. Finally, there are two variations of how you can call new, and corresponding variants of delete. To create an array, you call new with the size specified after the type in square brackets. Memory allocated this way should be deallocated using delete followed by empty square brackets and then a pointer to the memory to be freed. I hope this video has been helpful. Feel free to ask questions in the comments and I'll do my best to answer. Next video, I'll explore how to use new to dynamically create an array and resize it. Hope to see you then.